Hello teacher, my name is Takchan Sitha. I come from Group I365D and today we will talk about project 2 which is about CPU. These are our team members. We have Sreng Sophie Kanya, Takchan Sitha which is me, Tatat, Tang Nakri and Soksana. These are our table contents. First point about introductions. This project feature on designing and simulating a 16-byte CPU using SIG reverse. It simulates basic operations such as load, store, arithmetic operations, and end using custom control units and an ALU. The objective of this project is to make sure the implementations and integrations of the components in the CPU function correctly, and it also can execute instructions through a control instruction cycle correctly too. This is now we move on to the second point, which is circuit overview, and this picture is about the control unit of our project. The control units made up of main part, which are sequencers, instruction address register, RAM, instruction register, opcode decoder, command block, register A and B, ALU, multiplexer. And the function and its functionality is performing the three main phases of CPU, which are fetch, decode, execute, and repeat it once the execution is end. Next point is the detailed explanations. First components is sequencer. Sequencer is a control circuit that produces a timing signal S0, S1 to S4, and its role is control the timing of instructions execution, like fetch, decode, and then execute. The flow of this component is that each clock cycle advances one step from S0 to S1, which allow one micro operation at a time. And first it starts from S0 being high, while it is 1, and after the clock cycle ends, it becomes 0 and the S1 become 1 instead, and we repeat it until S4 become 1, and once it ends, it will repeat to S0 become 1 instead. Next is instruction register. Instruction register store the address of the next instruction to fetch from RAM. The role is to point where in the RAM the next instruction is and send the RAM address to the RAM. After each instructions, the IO or instruction address register increments by 1 in order to fetch the next address of the RAM inside the RAM. Multiplexer 8 to 4. It switches between one of several inputs, data inputs. The role is to choose address sources determined by the switch inputs through with RAM control signal. Flow. The first 4 bits A0 to A3 are the address of the RAM, and the last 4 bits B0 to B3 are the new address for the RAM to load data after the opcode phase. RAM. RAM it is a memory module used for both instruction and data. Role. Instruction fetch and data storage. The flow of RAM. The data in the RAM will load according to the assigned address and is written in the new data when the store A signal is true. And the address where the new data is being written will have the value inside there and overwrites the past address. Next is instruction register. Instruction register is temporarily holds the current instruction fetched from the RAM. Role is splits instructions into opcode to decode and address to control parts. The flow is to load signal take from the RAM and store it and send bits to other components. Opcode decoder is a logic block that decodes the opcode part of the instructions. It determines which operation to perform such as load and store, and send control signal to the command block. We have 8 inputs: A, B, C, and D. A being the least significant bit, and D being the most significant bit. A, A, B, A, B, C, D is the opcode, which we take from the most 4-bit significant, most 4-bit significant bit from the address of the RAM to determine the instructions what it want to do, and we take from the input of A0 to A3 is take from the 4-bit least significant bit from the RAM. It will be the operand which determine where the executions of the instruction is. Register is a storage that's to store data inside CPU temporarily. Its role is to hold data temporarily during the executions of instructions. And the flow is to get 4-bit input from somewhere like RAM or LU, and then we store, and then we temporarily store them for execution like add or sub operate or store A operations. And next we have ALU, which is arithmetic logic unit. It performs arithmetic operations such as additions and subtractions. The role is to take input from both, which is the A and B, and produce result for the output. Here is the flow. After the calculations is complete, the output will be stored in register A, then later will be stored in the RAM to the designated address. And how do we control the signal if it is additions or subtractions? It is through the control signal. Additions, it will be 0, 1, 0. Subtraction will be 0, 1, 1. Next is multiplexer for address. It switch the selects one of several data inputs. The role is to choose data source, example from ALU outputs or from RAM, and it's driven by clock and reset outputs. The outputs will be determined by the selector inputs. 0 is from, it will be from RAM, and if it is 1, it will be from ALU. Flow, if the read RAM signal is false, then the selector is true. So the input to register A and B is from RAM, otherwise it is from ALU. Next part is demonstrations. Before we going into our demonstration, here we need to know the key feature first. So for our project, we design our own opcode instruction as listed, and like load A, it will be 001, load B will be 0010, and N is 1111. Here is the explanations of our data, which we will load into our RAM. At address 0, it will load A data, which get data from address 2, which its value is 7. Instruction load B is from address 3, which the value is 3. Instruction 4, it will perform additional operations, which take the data from register A and B and plus it, add it together, which is 10. And then with address 5, with instruction is to store A, which the instruction we want to store is address 4. Address 6 is perform subtraction executions operations, which is A minus B, and because the register A from add is written from additional, which is 10, so it will take the input from A and minus it together, which equals 7, and then store the value 7 to address 5, and the address 8 is when we end the operations which we stop the CPU to function completely. Here is our data. We load, call them in our check. You see that the data is correct. Then we will run. The first is load A. We see that the load A register has been loaded successfully after the opcode decode and to execute phase. And this is the S3 is stop phase and the S4 is just to give more time. And then to S1. S1 is load B. We see the inputs load B is enabled. So we decode it. It is load B. And then execute it, which is read from RAM, read the data value from RAM, and return it into A. We return the data into B, which is value is 3, so it is correct. The value of there is nothing because it cannot do anything. Address 3 is also cannot, it just store the value of number 3. And then we go into add. Opcode decoder, you see that add is enabled. We decode it and then execute phase. Execute phase, we add value read A and read B is enabled, and then we add together, which is number 10. And then we store it into register A. Store it inside register A. And next is store A. Store A is enabled. Next, we want to check if it is correct. The instruction is store A at address 4. 0, 1, 2, 3, 4, number 10, it is correct. Next is sub operations, it is number 7. It will store number 7. Register A is number 7, correct. Next, we move on into store A. Store A, we dump data to check. It will be stored at address 5. So 0, 1, 2, 3, 4, 5, 7, correct. And then once it is to the latest operation, which is end operations, the end operation will be enabled true, and then we go into NOT gate, which disable the sequencer, so it will not do anything at all. It will not work. This is the end of my demonstrations. Now we will move on into our conclusions. This project focuses on designs and simulating a basic CPU architecture using digital logic components. It can perform the 3 phases, which is fetch, decoding, and executing. The project outcome is that it is successfully doing arithmetic operations and memory operations, and this can also gain clear understanding of the cycle of CPU and how control signal guide data flow. Our final thought is that it gives a hand-on experience in CPU architecture and digital logic design. It's also understanding how basic components work together. The biggest challenging is the control units and timing logic, but it is also most rewarding part once it works. And this project show that even with simple part you can simulate a real working processor. This is our member and responsibility. Thank you.